Hello everyone, my name is Adam Dziedzic, and today I have the pleasure to present to you our work on increasing the cost of model extraction with calibrated proof of work. This is joint work with Mohammed Ahmed Kalem, Yushan Nu, and Nicola Paperno. Nowadays, we collect enormous amount of data in form of audio, images, or text. Users can provide this data as inputs to machine learning APIs to label them. Behind the scenes, the creation of such ML APIs is a costly venture. First, it is hard to collect and label data. We need ML experts to tune model parameters. And finally, we also need expensive equipment such as GPUs or TPUs for training and inference. It was reported that a single training run of the GPT-3 model costs north of $12 million. However, the querying party might be malicious, with the goal of extracting the model behind the ML API. The question is how to defend against model stealing. Current active defenses either truncate the outputs or perturb them to poison the training objective of an attacker. Passive defenses use a difference in the distribution of queries made by an attacker and legitimate users. These defenses stop answering queries if they detect adversarial inputs. Reactive defenses are applied after the attack happened to detect if a model was stolen. Finally, we propose a novel proactive defense to make model extraction more difficult by requiring users to complete a calibrated proof of work before they can reach model predictions. Our defense prevents model extraction from happening rather than detecting it post hoc, and our defense does not introduce a trade-off with quality of the model outputs. In the standard model stealing scenario, an attacker sends queries to an ML API, and the victim model returns some form of outputs, for example, labels or scores. These outputs are used by an attacker to train the stolen copy of the victim model, and this is done at a much lower cost than training the victim model from scratch. In 2020, Microsoft published a survey in which they ranked model stealing among the most severe attacks against machine learning. The first step in our defense is to estimate privacy leakage the client's queries incur from the victim model using differential privacy methods via the Pate framework. Next, we generate a puzzle whose difficulty is calibrated using the estimated privacy cost. Next, the client solves the puzzle and sends the solution back to the server. The server verifies the solution, and if it is correct, we return the label. To generate the puzzle, we use the binary hashcash algorithm. A server sends a challenge string S to a client. To solve the puzzle, the client has to brute force search for a suffix X that gives hash with at least a specific number of leading zeros. In general, the more leading zeros are required by the server, shown on the x-axis, the more difficult the puzzle is, and the higher computational time for the client to solve the puzzle. And we showed it on the y-axis in the graph. Then we calibrate the difficulty of the puzzle using the privacy cost. This increases the cost of attackers' queries that reveal more about our training set, but it has negligible impact on legitimate users. So first in our defense, we set the privacy cost for legitimate users. Next, we measure the privacy cost of queries for all other users, and the model stealing attacks such as Jacobian or copycat incur higher privacy costs than a legitimate user. Finally, we map the privacy deviation to the puzzle difficulty. Now, how does our defense perform? We compare the accuracy of the stolen model against the time in seconds to run the queries. For a legitimate user, the increase in query time is maximum 2x. Instead, for the attacker, the cost increase is much more significant. For instance, a copycat adversary faces 100 times increase. In conclusion, we design a new defense against model stealing attacks that increases the cost of queries instead of lowering the quality of model outputs. The privacy cost is used to measure the information leakage from the victim model. We calibrate the cost of queries according to the privacy cost. This allows us to increase the cost of queries that reveal more about our training set making it harder for an attacker to extract a model, but easy for legitimate users to continue querying the model. We observe a negligible overhead for legitimate users up to 2x, and a very high increase up to 100x in the querying cost for attackers. With that, I would like to thank you for your attention.